suggest we move on to the next chapter, chapter number 6. I'm going to create a new script for this. So a relatively long chapter, and the point here is to explore different tools, different kinds of plots, different transformations, different data reduction methods, or clustering methods that are regularly used on biology or high throughput biology data, and to see how we can apply these, learn the R functions to apply these, and how we can extract different information to further explore and visualize and understand the data. Again, I need to check that I have my data. Don't. Nat, excuse me, do we have access to the Google Drive here on this computer?
What?
Access to the Google Drive.
We should, yeah.
So it's going to be this one right down here, the main institute.
Thank you very much.
Yeah.
So I suggest, in case you haven't done it, yesterday Kaylee added this data.zip archive with all the data sets that we need, those that we generated on the fly on Monday, but it's probably easier to have them on locally. So let me download this file, and I'm going to unarchive it and put it in my data directory. So it will be easier to load them. These are all the data files, all the data sets that we briefly saw yesterday. Okay. So the IPRG that we created from here, this one, and then we converted it into wide format, or reconverted it into long format. I don't remember what the 4 and 5 are. Yeah, so all these are those that we will be using, either that we will be loading here or that we will be loading from existing packages today. Is it okay? Do you have access to all these data, to all the data sets? So I'm going to library, so I'm going to start by loading data and IPRG 3. And now we're going to simply use 2 files, or 2 columns thereof, the second one and the third one, and I'm simply going to call these to X and Y. Again, I'm going to use base R here for convenience. Here is the scatter plot that describes the intensities for the second and the third sample from the scatter plot. And this is a typical distribution of intensities that we have for proteomics, transcriptomics, and so on, where we see that most of our intensities are kind of squeezed towards the low end. We can also look at these by calculating the density of all these. So if I do density of X, I will get an error because I have missing values. Again, something that happens very often. So here for convenience, I'm going to remove all my missing values with NA dot omit. Okay, to calculate my density that I can now plot directly here. And again, we have a huge majority of our intensities at the very, very low end, and then a couple of really high intensity values. And coming back to the scatter plot here, this very often gives a false impression of very good reproducibility, although it's not the best measure of reproducibility, of how well we manage to reanalyze or re-measure the same sample or similar samples. And it's much more representative of the actual data to log transform the data. So here, using plot, I don't transform the data, but I ask the axis to be converted to the log scale. And now, on the log scale, we start to see the actual variability at the low end. It's a much more representative visualization of what actually happens in the data, and that we have variability, and that variability is here at the lower scale, as opposed to this, which gives us a too positive impression of our data. And actually, many of the normalization methods that are used, maybe not that much in proteomics, but in other high-throughput data sets, systematically convert the data on the log scale. So if you want to generalize this practice of doing our scatter plots, for example, here I'm going to use only a subset of our data. We can use the pairs function. So we have five samples, and the pairs function will create this 5x5 matrix with all possible pairwise combinations. And again, I can pass here the log equals xy to convert my axis on the log scale. And here we start again to see the actual variability underlying our data. So it's possible to parameterize the functions that are used to generate these. There is a whole set of these so-called panel functions. So there is a panel upper function to customize the figures that we want to have at the upper rectangle. There is a panel lower if we want to get different figures on the lower triangle, and there's a panel diagonal if we want to change what is observed here on the diagonals. So I suggest you try this out a little bit, and there is an example in the lecture notes here, and I suggest you can take it as it is, where here we create a new function called myPanel. So this function always takes two inputs, x and y. The values, the two vectors, x and y, that are used to generate figures. And then in here, you can use them the way you want. And so here I regenerate my scatter plots with points x, y. But I define my color to use some transparency to avoid too much overplotting. But then I want to add a grid, and I want to add a diagonal line that crosses the axis at 0 and with a slope of 1, with AB line 0, 1, and here I plot it in blue. So by defining this function here, I can reuse it in pairs. So this produces my matrix of scatter plots. But here I say that my upper panel, the way my figures in my upper right triangle should be generated, is not with using the default function, but using my panel that I defined here. And if you look at the documentation of question mark pairs, you'll see additional panel functions that have been defined, for example, to generate histograms, to calculate correlations, and so on. And this can also be used to define your upper diagonal or lower panel. Okay. So I'll give you a couple of minutes to explore the pairs function and to customize some of these plots. So here's one example, but if you look at the documentation of pairs, you'll find other ones. Ranbridge quota of 3 sticky notes, but I suggest we carry on unless there are any questions. So Stephen yesterday mentioned overplotting quite a bit. Indeed, here we take, actually I'm going to say x10 log 10x, and have this out of the way, y10 log 10y. And so indeed here, there's quite a bit of overplotting. So base R apparently does, in this case, the right thing compared to ggplot2, and it uses the circles, so it helps us to distinguish, tell apart some of this overplotting. But of course, when we have a lot of data, which is generally the case, there is no way we can stop points to be on top of each other, to hide each other. So one simple approach would be to specify the colors. And so here, using this notation where they all go by 2, this is hexadecimal notation. So this gives the amount of red in the channel, green and blue. So if you leave them all to 0, I get black. And then the last one here that goes from 0, 0 to FF will define the alpha channel, how much transparency we want. Okay? And so this might help us to distinguish highly dense from low dense regions in our plots. But another really useful function in such situations is the smooth scatter function that would automatically convert or use a kind of a scale of blue from very light when we have very few points to much darker when we have many points, and then the single points are still shown here as little dots in the figure. So if we have any points, that what we're interested in is the density of these points. Smooth scatter is a very useful function and very easy to use. Another approach when we're interested in density is to use binning, hexagonal binning, and the package hexbin allows to do that. And so, for example, here we could still using the X10 and the Y10, and this can be plotted immediately. Now, what we will have is that we will bin the data in little hexagons, and the color of the hexagons will reflect how many points we have. So, for example, like gray regions here are those that have only 1 point, and so on to the very dark and red ones that have over 200 points per bit. So again, if that's something that you want to highlight, hexbin is used. Can be used, and there is actually a geom hex loaded ggplot2, but there is a geom hex that depends on the hexbin package to generate these using ggplot2. Similar as we saw before for the raw intensities, I'm going to show this here, for the fold changes. So here I calculate the fold changes between the second and the third column of this IPRG data set. And here I plot the density of my raw fold changes that are centered around 1, and my log2 fold changes that are centered around 0. It is recommended to always look at your fold changes in log space, because now your negative, your downregulation, and your upregulation will be symmetric around 0, as opposed to squeezing all your downregulation between 0 and 1. And this is also what we will be using later on when we will produce volcanic plots. So, yeah. So still using kind of simple plotting techniques, but let's look a little bit at the at some of the Okay, I really seem to have a problem with my online data. Did anyone manage to load, for example, the ALL data from that was downloaded? I have an error here when I try to do that. Well, if that also happens to you, it's easy enough. It's possible to regenerate the data from, or the subset of the data from the original ALL data using these lines of code that we looked at yesterday, and I'm going to show you where they are in the lecture notes. So if you go second chapter with example data sets, section 2.5 ALL data. Here is the first chunk of code. It'll take only the subset for the two groups that we want to compare, and this is the analysis to calculate our fold changes and the p-values. here is my ALL data, an expression set, and the frLabel function will give me the feature variables that I have, the different columns here that annotate all my genes. And so let's look a little bit and do interpretation of these p-values that we have. So we have 12,625 individual genes for the 79 samples, and so we also have 12,625 p-values that we can extract by accessing the whole data set, and from that data set extract the p-value variable. Here it is. And so whenever you do a test, a statistical test, you calculate p-values, the most important thing is to look at this distribution of the p-values. So here they are. That's the distribution of all, 16 or 12,000 and so on p-values. And if everything works according to plan, if you have a proper experimental design and you expect to, and you observe some features that are differentially expressed, this is what you would expect to see, an increase in enrichment in small p-values. It's important to put this into light. Sorry. So this is the type of distribution of p-values you would expect if there was nothing significant in your data. Okay? A uniform distribution where you are as likely to find high p-values, mid p-values, or small p-values. So if there was nothing significant in your data, one would still expect to see some small p-values. And this is random data, but this is also the distribution of p-values we would expect from a real experiment. And here, when there is indeed some signal in your data, you need to be able to observe, before any adjustment, an enrichment in these low p-values. And of course, after doing your adjustment for multiple comparison, you will take into account the fact that you don't have a single test, but you have many tests, and that your p-values need to be adjusted. But it's only acceptable to move to the adjustment of p-values before kind of quality checking your p-values, your distribution of p-values. And here is an example. Here's an example of the kind of things that can work, or that one can obtain. So example A here, anti-conservative, that's when everything works according to plan. There is a substantial enrichment here, and even after, or one can expect that even after the adjustment, you will still have some features that are differentially expressed. So here's the anti-conservative best case scenario. Another one is uniform. There is nothing in the data, or at least nothing that can be identified by doing feature-wise t-tests. Here are other weird, kind of more unexpected distribution of p-values. For example, this bimodal distribution. And even though there is an important increase here for low p-values, And even though it's likely that even after an adjustment for multiple comparison, you might still retain some of these significant features, this is a weird pattern that should stop you from there. And adjusting these data for multiple comparison, when you have this bimodal distribution, will negatively affect your adjustment for multiple comparison, because the adjustment expects a distribution like this, okay, or uniform distribution with ideally an enrichment for small p-values. So clearly, if you have something like this, best to stop and try to understand what happens, and this could be the case if, for example, you did a one-tailed t-test instead of two. But clearly, if you see something like this, you need to stop. Okay, and even more so here, it could look like, oh, something's wrong anyway, I won't have anything significant after my adjustment. But again, this might point out to something weird in your data, an enrichment of features that show really high p-values. For example, if you have kind of a systematic pattern where you have features present in one group and absent or constant in the other group, this kind of conservative distribution of p-values is certainly something you need to stop at. And it doesn't mean there is nothing in the data. There is something, it is a sign that maybe your data didn't meet the requirements of the test. And so there might be some interesting signal, but clearly another approach is needed. It's also possible to have a kind of a sparse distribution of p-values. That would typically be the case if you use a kind of group bootstrap method, and where you don't have enough repetitions and you don't have a proper sampling of p-values. Again, that is weird, and it's probably the procedure that is not adequate for what you want to do. And here, very weird pattern. It's a bit unclear what happens in these data. But again, anything that is not uniform, it's sad, but that's the data, or anti-conservative, should point you towards quality controlling your data and trying to understand why do you find these bizarre p-value patterns. So, extracting your p-values wherever they are and plotting a histogram is most certainly the first thing to do after running your statistical test. Extremely useful and extremely important. So we have our fold changes, we have our p-values, we have QC our p-values. So the next step is typically to produce a volcano plot. And so depending on what functions or what packages are used, there are many packages that will calculate these automatically. You might just say plot volcano or volcano plot. But it's also useful to be able to generate these yourself by hand. And let me come back here. Labels. And with our ALL data set, we indeed have our log fold changes, our p-values, and our adjusted p-values. So let's produce this volcano plot ourselves. So I'm going to create a temporary variable log fold change to save myself some typing later. $log fold change. So here, oh yeah, sorry. Yes. Yes.
If it looks anti-conservative, if you just click plot the p-value, does it still need the adjusted p-values?
Here. Yes, yes. You absolutely every time must do your p-value adjustment. And so if you have a distribution like this or like that, then you meet the requirements for your p-value adjustment, because these procedures expect a kind of a uniform distribution of your p-values. if you have something like this or like that, then you should stop doing your adjustment, irrespective of the fact that, not because, or anyway, you're not going to find any results, significant results after your adjustment, but you should stop because the requirements are not met. These distribution of p-values are weird, are odd, and so it's probably worth understanding why do you get this unexpected distribution of p-values. It might be that there is signal, there are interesting patterns in your data, but maybe the statistical procedure was not appropriate, so yeah, you need to stop. But indeed, even if you have this, you absolutely have to do adjustment. You always have to do adjustment.
That's a requirement to do adjustment, procedure adjustment.
Yes, the requirement would be to check that your p-values have an expected distribution. And if you have a uniform distribution after your adjustment, you will probably not have any significant results. And that's maybe a kind of extreme case where you have a really high enrichment. And very often it might be somewhere between this and that. But it's, yeah, absolutely. To QC your p-values before proceeding. So here is my here are my log fold changes. Now, centered around 0. Here are my, I'm going to call this adjusted P. So I'm going to extract them again from the ALL $large.p.val. So here's the distribution of my adjusted p-values, so that's the effect of my adjustment. So here I have this weird distribution, but these are my adjusted p-values, so this is the effect of the adjustment. The quality control should be done before adjustment. And so now we can plot these. So we want the log fold change. The x-axis, we want the adjusted p, actually what, minus log 10 of these adjusted p-values. Change. Look, and so here it is. So the most interesting features, so we could set arbitrary thresholds. So these would be vertical line equals c minus 1 and 1. That you might want to consider only the magnitudes greater than 1 and smaller than minus 1. And again, an arbitrary threshold could be minus log 10 of 0.05, which is a commonly used threshold for p-values, even though it's completely arbitrary, or 0.01. Here they are. But the importance of the volcano plot, or the advantage of using a volcano plot is that it stops us from using any of these hard thresholds, 1 to minus 1, smaller than 0.05 or 0.01. I don't know. What about this point here? Okay, it's lucky enough to be just above, so it's a winner, and this one that is just below is unlucky and is a loser. So fold changes or p-values or any other metric that you calculate are only a way to sort or to order your results. Okay, so if you have 20,000 features that you analyze, the number of those that are interesting depend, of course, on the long fold change of the just p-values, but they also depend on the money and the time that you have to validate some of these. And so this is really only a means to identify interesting candidates. And if there is a lot of money and a lot of time, you might want to do a lot of downstream analyses because you can afford it. And if you don't have lots of money and lots of time, you might only choose one or two. And the number of candidates that you will choose does depend on your resources, but also on how much risk you are happy to invest in pursuing false positives. And so typically, irrespective of these hard thresholds, those that are most interesting are those that are towards the right and the left, and those that are towards the top of the figure. So irrespective of the thresholds, irrespective of these, the actual adjusted p-values here, and irrespective of the fold changes, a scatter plot, a volcano plot like this clearly indicates that these two are the most interesting candidates because they are outliers. And then there is this population of points, and it's interesting. Maybe these ones, now depending on where we are at the p-value, and then maybe these are also interesting, but they are not as kind of outliers as the other ones are. So again, it depends how many results are you happy to chase, and that are needed for you to proceed in your scientific investigation. Same thing, if negatively or downstream regulations are important, well, the best candidate would be this one, and then maybe this one. Here, clearly, in terms of reproducibility of the results, this one is not as good. But most likely, anything beyond that one will be more critical, irrespective of the fold changes. And so if you have a knockout, and this one happens to be your knockout, well, these are the results. So if you know that it's a knockout, or it's something that is supposed to be downregulated, it's not because it's below these arbitrary thresholds that suddenly biology breaks down. And so the advantage of this plot and any similar plots really is to go beyond thresholds and give you an idea of whether some of these points are outliers. And if they are outliers, then they will be interesting. Okay? Yes?
So I'm wondering, can you define in the code like what method you use to adjust p-value?
Yes. So here, Lima automatically uses, if I remember well, Benjamin-Horberg, I think, to do the adjustment. And it's done automatically, and that's very often a very sensible method to use. There is a function called p.adjust. Here, let's see. So the p.adjust function that will take a vector of p-values and then it will adjust them. And the methods that are commonly available, or that are available, is Benjamin-Horberg. We have the Bonferroni, but FDR, so a whole set of methods that are needed. I guess Benjamin-Horberg, the default in many methods, is fine. That is, I think, not what's going to make or break your analysis. You need to do an adjustment, and I don't know, Kai, if you have a different experience, but I think they should all be very equivalent. So the Bonferroni would have a different impact, and so the difference to get an intuition of what happens numerically, if we have all our p-values ordered from the smallest one, p1, p2, p3, p4, to pn, what Bonferroni is going to do is that it's going to, for all of these, do p1 times n. Okay, so if you have 10,000 genes, the smallest one will be times 10,000 times thousands. And of course, they will make sure that they don't become greater than 1. So that would be one for only, and then in addition to that, numerically, Benjamin Holbrook is going to divide by the order of the p-value. So that one will become p1 times n divided by 2, that's 2, p3 times n divided by 3, and so on, and then the last one, pn times n divided by n, so the biggest one, which is probably 1 close to 1. But yes, the Benjamin Holbrook is, I think, a really good choice, and I have absolutely no idea why another one would be better or worse. In proteomics, very often the kind of Q-value method is used. I think they should be to provide very, very similar results.
I'm wondering if they can label some of the interesting points on the volcano plot.
Pardon?
Is it possible to label some of the interesting points
Yes.
on the volcano plot?
Yes. So let's take this one. So you could highlight any point if, for example, you have an additional variable. So if it was a ggplot2, you could have a column that says, interesting, not interesting, or something like that. But here, what you can also say is using an if-else statement. And for example, say if adjusted p is smaller than 0.001, for example, then my color should be red. Otherwise, I keep it black. And so this one will kind of on the fly. Here's color. The default color is black. Let's maybe execute just run the code independently. And I'm going to use a small threshold here to get I'm going to say at this, and hopefully no. So these are my 21st adjusted p-values. And I'm going to use these. So I take all my adjusted p-values, and I'm going to check whether they are smaller than 0. And here I'm not going to take 0.05, but I'm going to take 0.4, because here I have one value that is 0.33. So I'm going to check each of these and ask whether they are smaller than 0.4, and if that's the case, then I want the red to be returned, otherwise I want the black to be returned. And so this line allows to easily convert quantitative values that meet these requirements with a red or black, and indeed we have one red somewhere here, the 9 value that corresponds to this one. This is, oh, yeah, this one, and then there is another right here that corresponds to that. So you can use this on the fly, for example, to color your points. Now the kind of the poor man's interactivity here would be to use the identify function, and either later today or probably tomorrow, we'll see how to quickly, or not so quickly, develop interactive applications. But doing this sometimes requires, extra time. Because you don't want to use them once very quickly, but if you really develop an interactive application, it's ready to use and reuse it systematically. Sometimes you want to kind of quickly get an idea over what is this point and that point. So you could use dplyr, for example, to select those that have an adjusted p-value y equals 10 greater than something. But you can also use the identify minus log 10. Increase this a little bit, and I'm going to store the output here, for example, in a new variable k. And so this allows me to click on this figure, click there, here, and here, and then right click, finish here. And now I have the index of all these points, so I want to identify the points on this figure. I have to provide the x and y coordinates of all my points, and then on every point that I have created, it returns the position, the index in these two vectors. So I clicked on these three, and then their index is highlighted. And I think I also must have clicked on another one. I'll click here at the top at some point. And so their indices are shown here at the top. Okay, so identify is kind of somehow a poor man's version to quickly get some interactivity or identify specific plots on your figure. Another interesting concept related to visualization is the following. So that's part of the study published in 2013. And so they did a linear modeling of a data set. And the interesting feature or the interesting result in these linear models are the slope. Okay, so is it a little bit like here, a horizontal line, or do we start to see a slope that is of interest, a large one or a large negative one? And depending on the result of this slope, that would be an interesting or significant result of interest. And so what they have done here is kind of to treat the plots as statistics. So they have generated simulations based on their data, and then they have repeated the same analyses and generated the same plots. So here these are 20 plots, and only one of them corresponds to the real data. And so the idea of this technique is to say, can you spot the result that is based on the real data? And if you can, that would be an indication that is not based on any formal method, like calculating p-value, but would be based on our capability to identify interesting patterns visually. But if we are not able to spot the correct data set here, that it's kind of anonymous within all the other simulations, then that would be an indication that actually maybe there is no pattern of interest. And I don't remember which one the real result is here, but clearly it would be a little bit difficult here to identify all. There is no clear outlier that seem to be more interesting than others. I don't know. I really don't remember, but if this is the correct result, well, it happens that under the conditions of their simulations, they got to other figures that vaguely look like as interesting as this one, if that was the real result. So I have done the same thing with the ALL data set, where I have repeated all the analyses and I'll give you a little bit of time to look at the code. So I have repeated the lemma analysis, but I have always done permutations of our sample groups. So we have two groups, the healthy and diseased, or those that have cancer. And I have permuted all the groups and repeated statistical analysis and plotted the histogram of p-values that we obtained. And so can you spot here what the most interesting distribution of p-values? One of these 9 is the real data set, and all the other ones are the result of simulations. I imagine that you all agree that this one looks the most interesting distribution of p-values because you have an enrichment of small p-values. But interestingly, here this one doesn't look too bad, not as an important of enrichment, and maybe we wouldn't, no p-values would survive the adjustment of multiple comparisons here. But here I think we have a clear winner. This one looks interesting, and indeed that is the correct result. Any questions so far? Okay, so the next section is to see a couple of tools to visualize intersections and then test the offset R visualization method that we have seen yesterday. And so to generate some data, I'm going to extract the feature names, so the G names of that CRC data set that we have as an MSN set, and I'm going to sample some of these, and maybe 35. So if I do this among the, I don't know how many tens of thousands of feature names that I have in this data set, I'll take randomly 35 out of these. So this returns a vector, length 35. And I'm going to replicate this, for example, 3 times. And store this in a temporary variable x. I'm going to say simplify equals false because I would like this to be a list. So here I have 35 taken at random, 35 taken at random. However, what I'm going to also do is to make sure that they are taken at random, but that I have an idea of what to expect. So I'm going to set my seeds. Go. And that typically reflects what we would have if we have replicates and we want to see to what extent do we identify the same set of peptides or proteins and so on. And so before starting with offset R, I'd like to show you, because sometimes we need to do Venn diagrams, and there is the venerable package that I think is can be quite useful. And the function, the main function here would be Venn. And the input to Venn is, just here, is a list. And here is how this output looks like. So I have 3 sets as input, and I have only one that is present in, 10 that are present in set 1, 9 that are present in set 2, 6 that are present in the intersection between set 1 and set 2, and then 12 that are present in the intersection of the three sets. So we can plot V here to generate these Venn diagrams, which are, I think, are particularly horrible. I don't know why they choose these kind of colors, but again, the point here is not to produce nice figures, but if we want to find Venn diagram, generated this Venn object, and plotting it gets us quickly what we want. And I find also this result interesting here, that is very similar to the kind of the first dimension of the offset bar diagrams that tells us how many, we don't need to look it up on the figure here, but it tells us how many we have in the respective intersections. And something else that is useful here is that if I want to access the features in these different intersections, I can do this here with the V at sign intersection sets. Okay, so V is my Venn object, and this accesses this slot. At is a new kind of cryptic sign that we haven't looked into detail, but it allows us to access one specific slot of that more complex objects. And here's the result. And here, for example, 100 gives us the features that were unique to the first set. And so we can here, for example, use 100 to access specific things. So clearly the visualization here does not scale to many sets. But we could still, if we had 4 or 5, still kind of look at these results and access those of interest. Having said that, if you have many sets and they are large, Venerable is going to become too slow to actually use. But in many, many cases, we don't have tens and tens and tens of sets. And so it can be useful. But as we have seen yesterday, the offset R package is really, really useful, really, really interesting. And so very often we have our sets of interests in different lists. And so there is a function that says from lists that will convert at our list of interests. So this was the first set, the second set, and the third set. And here it tells me that the different observations, whether the different observations are present in the 3, only in the 1, or the first and the third, and so on. Okay, so that's the from list function that takes your list of sets and converts it into this format that can now be used with offset. So, okay, could you try on your computers? Because this clearly worked on mine when I recompiled the lecture material. As shown here. Okay. So could you try, please? So I'm going to let you test offset on your own, but my suggestion would be to really see the advantage of offset. It's not to replicate here only. Repeat this 3 times, but maybe do it 5, 6, 7 times to really get a feeling of how offset R is useful in cases where Venn diagrams completely break down. but could you please let me know if this works? For some reason, this does not work on this computer, but it worked on my laptop when I tested it. Otherwise, this figure would not have been generated. Could somebody tell me yes or no? So could you put a green sticky note of if, when you generate this test data set here, based on the feature names of CRC, or you can generate any data set that you want. Oh, is it maybe because I need to set letters? Yeah. Oh, okay. Sorry about that. So what is essential for offset R is to make sure that the elements of your list are named. And so here I have arbitrarily named them capital A, B, and C. And so here it is. I don't need to explain what this visualization means, given that we had an extensive presentation of offset R yesterday. So as an exercise for you, I suggest that you do the following. Let's try to do something more interesting. I don't know, maybe 10 and 50 here. STR. So let's say we have 10 replicates of our experiments. We want to see to what extent we are able to identify the same features multiple times. We convert this to, we set the names, that is important. We convert it to the offset R format, and so here's the result. So I'll let you have a play with it. And so in the notes, I also briefly document how you can reorder these. And the cardinality for your different intersections, or the cardinality for your input sets. Okay, so I'll give you a couple of minutes to explore this a little bit. And could you please put your green sticky notes up once you're happy and you had a chance to explore offset R. Yes. Pardon?
What is this horizontal?
Oh, so this one says that I had, what was it, 10 sets, A, B, C, D, and so on. So by default, it only plots, it takes 5 of the sets, but this is something you can parameterize. And it says that actually in my set J, I had 50 observations, in I 50. So in this case, because I created them so that I always sample 50 feature names. These bars here are all the same length, and they indicate that I have 50 observations in each set. If here this was not always 50, then we would have different length.
And the number of horizontal bars and number of items that we have.
Yes, and so this tells me that in the element it is only present in number J, I have 2. I have 1 that are only in F and in H. But for example, if I look at those that are present in 5 of those sets that are plotted here, I have 12. Okay, and so there are some ordering parameters that allow you to kind of change this. So here, these are ordered based on single set observations up to those that are in all intersections.
Right.
But this is something that here can change.
So one question I was asking Alex yesterday as well regarding this, that if we have k categories, then the number of bars that we can have is 2 to the power k. So based on your experience, have you dealt with such scenarios where you have, for example, even 50 categories? So number of possible pairwise comparisons or number of multiple bars that we can have is 2 to the power k, and we cannot see all of those together, of course.
Yeah.
So what do you do in those situations?
So as you can see here, by default, it will only take 5 sets, and this is something that you can change. Okay. So by default, it limits the number of sets that you have.
And we can choose which
Yes.
factors I want to take.
You can choose the number and which ones. So I think the number is probably those where you have most observations, but in this case, I have 50. It's random. So generally, you are not necessarily interested in a set that maybe has only one interaction with another one, and that one you could drop. And so here you will then choose those that are of interest, and by default, generally, these are those that have the highest cardinality, to display the part of the data that you're interested in. One thing that is important is that when your data is really that big, and in this case you have many sets with large cardinalities, it's just too big to visualize. Clearly, it doesn't work with Venn diagrams. So some people, like Alex and Ias that will meet tomorrow, they have developed new visualizations that allow to scale up. But then again, if you grow your data even more, even these ones at some point will fail. But I think in my experience, generally, the more data you have, the more pre-processing you will need to do to summarize that data to be able to visualize it effectively. And here would be, for example, to drop the sets that have very few observations anyway. So yes, it doesn't scale. In theory, it doesn't scale up to really, really big data sets. But in practice, I think it's rare that we really need to see, 100 sets here. And if it's the case, maybe you need to do think of something specific to your problem.
Like you said that the function observer by default chooses the elements to show which have maximum number of interactions with one another.
So let's look at question on offset. Okay. So you can define whether you want. Okay. So here n intersects, and sets will how many sets do you want to present? How many intersections do you want to present? So you will be able to fine tune that. And so what else do we have? I think, like in many cases, most visualization work for standard out-of-the-box data sets. But if you really have something new, that is bigger or more complex, you will have to explore the data and maybe devise your very specific visualizations, or summarize your data with the same things like dplyr or dimensionality reduction techniques, transform your data so that it fits a convenient default visualization. Or the other spectrum is to develop completely new interfaces, interactive interfaces for your data to really be able to explore and identify interesting features. But that becomes research and development, right? You don't have a box standard data set that fits to what we have. And then maybe you would need to collaborate with somebody like Alex that we saw yesterday, where they are really going to devise a dedicated interface. And that would be the total other end of the spectrum. But before that, you use kind of simple tools, simple visualization to get an idea about your data set. And slowly you will come up with a visualization that fits your needs. And if not, then it becomes a project on its own.
Right. And so regarding the resources, I think you mentioned the book, right, by Tuft. And the visualization.
Steve mentioned, right? Yes.
Okay, sorry, Steve mentioned. So those books are not going to tell us about this kind of ultra-high-dimensional data sets where number of features, either the number of features are huge and the sample size is very small in those kind of setups. So I was wondering that based on today's age of cutting-edge research of these omics data sets, how useful those resources would be, which are like the textbooks kind of things.
Oh, so they will not give you, they will not address your specific problems, but they will lay out general principles of good visualization, okay? That you will want to apply when you start to fine-tune your visualization. Here what we do is kind of quick and dirty. We need to get an idea, we need to understand our data. And generally you do not have the time to really produce something that you would want to show or to use when you communicate, because that will take extra time. But first you want to read out the nonsense. So I think these books are really good resources to know how to effectively present something towards the end, or if you want to devise, develop a kind of an interactive application, then we want to
Make sure that those
to make it really effective. On the other hand, other tools that you would need are general data wrangling, general ggplot2, general machine learning and pattern recognition concepts. Because, for example, if we go back to the volcano plot, one really important feature that we need to produce a volcano plot are these p-values, and these are just p-values. So that's something that you would use statistics for to calculate these. And that's a way to then visualize your data. So very often, during your exploration of your data, you will come up with new metrics that you want to calculate that are a representation of why you generated the data. And these new metrics, and these could be p-values, these could be things like, we're going to see some examples in the afternoon. You will do some clustering. And then you'll say, oh, this protein belongs to cluster 1, this protein belongs to cluster 10. And then the cluster belonging of your proteins is something that you will use, for example, to use colors on your figure. So very often you will need to do new calculations, calculate new things that you will have to come up with to annotate your plot or to present new features. And maybe you'll really have to come up with new visualizations. But very, very often we use scatter plots, bar plots, and start to align them or to add some interactivity. But yeah, I like to say that becomes a project of its own with time and resources. So for example, here I use n sets, and now I have 10 of these sets. And so at the end of the offset R section, I have also added a link to the Shiny, the interactive app for offset R, where you can upload your data yourself and generate these figures online with, I guess, some interactivity. Although I've never used it online. So we have a couple of minutes left until the coffee break. So I suggest maybe you can finish up this session with testing offset R, maybe comparing it with a classical Venn diagram. One thing I'm not sure is if from the offset, let's try this. So I'm going to call this, let's see if offset R returns an object. No. Okay. So one thing I'm not sure how to do in offset R, but I think that would be really useful, is to say, okay, I have, change this default back. So I see that I have 12 features that are present in sets, these ones, I would like to know which ones these are. So I think it would be, that's something that I think is very often useful after the first visualization, so you get an overview of the data. But very often I would like to know, oh, well, which one is it that I only have in F? And that would be the kind of graphs that I think should help us to answer that question very quickly. And I'm not sure how one could do this with offset R, but here we can extract immediately with the venerable package, which is not very beautiful in terms of visualizations, but I think is very useful in terms of accessing, calculating all these interactions and then accessing the features. But again, it doesn't scale for big data sets. And so after the coffee break, we'll move into more machine learning type of tools that we can use to visualize and understand our data. We'll see hierarchical clustering, k-means clustering, dimensionality reduction techniques, and see how distances can affect these patterns that we have. Okay. Right, thank you very much, and let's meet back in 30 minutes.